question last time. Remember this one? Yeah, as I know, this one. And yeah, here, yeah, this slide. Yeah, look at this slide. Remember, I asked you when we solve the differential equation, we remove that absolute value, right? We remove so I ask you the question why we can remove that absolute value. Right? Yeah. So let me. Yeah. So we complete that. Yeah. We are at the last step. This step. Right. Okay. Yeah. This step. But there is one question we haven't answered in class. So I ask you to think about it. Okay. Yeah. Because this question, in many situations in this class, you need to answer this question. Yeah. So when you solve question, yeah. All right. So you will have several questions you need to deal with this absolute value thing. Yeah. The question is, this equation, because after we do the integration here, by the formula, we need that absolute value. You cannot throw away. Yeah. Otherwise, natural log of a negative number is not defined. Natural log function cannot be applied on negative numbers. So that's the reason we use absolute value, make it a positive. Then you can use the natural log function. Yeah. But when we when we remove that natural log, we don't want to leave that absolute value function. We want to remove it to make the function simpler. Yeah. All right. So here you can see from that step to this step, we remove it directly. But you need to justify it. Why you can remove it, right? So here there is a question. You need to justify it. Yeah. Justify what? Justify inside absolute value, the whole thing inside absolute value is positive. Then you can remove it, right? Otherwise you cannot remove it. All right. So the whole thing inside absolute value, this part, must be positive. So you need to convince people 5,000 minus y must be positive. Yeah. So let's answer this question. Why? Y must be less than 5,000. This question. Okay. So the question is, why we have y less than 5,000. Right? So that question we need to answer. Okay? All right. Yeah, let me answer it. Yeah. Because here we do not have a lot of time, so I cannot give you a lot of time, Yeah. Because I ask you to think about it at home, not here. Yeah. All right. Yeah. So here, let me answer in this way. Yeah. We need to go back to our original question. Look at the given data. We need to do some analysis. Yeah. Here, when you do analysis, I want you to focus on the concentration of the mixture. Concentration, okay? Yeah. Or the density, concentration or the density. Yeah. So look at the density of inflow brine. What's the density of inflow brine? Can you see that? 5 pounds. The density. Good. Density of the inflow brine, 5 pounds per gallon. Good. All right. Then let's look at the density in the tank. At initial point in the tank. What's that density? Initial. Yeah. Good, 1 over 10, okay? Because 100 pounds over 1,000 gallon, right? That's the initial density, right? So in this tank, initial density, yeah, all right. 1 over 10, let's write 0.1 pound. How about that? 0.1 pound per gallon. That's the density, okay? You can see the density of these two places quite different, right? Yeah. Outside brine, very dense, right? Yeah. Much more dense than the inside brine, okay? All right. Then you think about when outside inflow more and more, although you know after stirring, yeah, then outflow, then mix them. What can you say? So brine with higher density mixed with brine with lower density in certain way. Any conclusion you can give me?
Well, the brine that was initially in the tank,
Yeah.
a higher density, and then
Yeah.
brine that was outside would get lower dense, but the mixture would be
Mixture.
more dense than the initial.
Yeah. Can we say this? The density of the mixture, you know, inside the tank can never be greater than outside density, right?
Yeah.
Because you can only bring down, right? After you mix, you can only bring down the density. You cannot lift up, right? Yeah. So can we say the inside density is strictly less than outside density? Yeah. All right. What's the inside density? At the time t, inside density in the tank after stirring. Okay. The amount of salt, we know amount of salt, right? Y of t, okay? Y amount of salt over 1,000, right? This is inside density is always less than outside density 5, right? Is it Y less than 5,000? Multiply 1,000 both sides. Y always less than 5,000. That's the reason we can remove absolute value. Okay?
Why can it not be equal to 5,000 as well? Is it just because it always approaches 5,000, never quite reaches it?
Yeah, never reaches 5,000, right? Yeah. You take average. Think about that. You take average. Inside always strictly less than. When you take average, how can you make equal 5, right? You use 5, do average with a smaller number. You know, keep doing that. It can be closer to 5, but can never reach 5, right?
Okay, that makes sense.
Yeah, you can infinitely approaches. Okay, the limit is 5, but it can never reaches 5. Okay, let's say in this way. So we are safe. Yeah. So it cannot be 0. Okay. Yeah. Strictly less than 0. Yeah. Oh, sorry. Yeah. I mean, yeah. You know it. Yeah. All right. Yeah. So here I explain this question. Yeah. So later, when you have the similar situation, you need to do the similar analysis. Try to do the same thing. Okay? Yeah. Because we are working on the real world questions, so we need to go back to our original question. Yeah. It's not just solving one equation, then you are done. You need to do a lot of work after you solve the equation. Yeah. All right, so let's move to the new topic. Yeah. So let me get out. Yeah, because I need to skip a few slides. Move to the new problem. Yeah, this is new problem. All right. Leaking tank problem. Yeah. Leaking tank problem, number 6. All right, let's look at the question first. Yeah. Question. Yeah, so this is the figure. Yeah, so you can look at the tank. Okay, yeah. Cylindrical shape. Yeah, tank. Yeah. Water inside. So here. Yeah, so the condition, first, diameter of the tank. 2 meters diameter of the tank. Yeah. And the height, height, 2.25 meters height. Yeah. And at the bottom, there is a small hole. That hole has a diameter 1 centimeter, cm, okay? 1 centimeter, small hole. Yeah. So water flow out. Okay? Yeah. Leaking. Yeah. Leaking. Yeah. All right. So now you can consider there is a velocity of the water. Yeah. What's the velocity of that water leaking out of the tank? Yeah. That velocity should not be a constant, right? Yeah. That velocity should not be a constant, because at the beginning you have a lot of water inside the tank, so the pressure is very high, right? Then the velocity of the leaking water very fast. But after the leaking goes on and on, yeah, so the pressure smaller and smaller, yeah, because the water inside the tank, the height becomes smaller and smaller. The pressure is smaller and smaller. Then the velocity also becomes smaller and smaller, right? So it's a function. Velocity function. It's a function of t. Yeah. All right. So then, initial height of the water when the hole is opened is 2.25 meters. Yeah, initial. Yeah. All right. So now we want to look at the question. The question is, when will the tank be empty? Yeah. You need to find the time. Yeah. Starting point 0. Yeah. So when you open that hole, yeah. So you clock it. Okay. When you open that hole, then you clock it. Yeah. Then, how long? After how many hours, the whole tank becomes empty? Yeah. We need to solve this question. Okay? Yeah. That's the leaking tank problem. Yeah. All right. First, understand the meaning. Yeah. It's very easy, right? Yeah. So here, everything is clear. Yeah. Yeah. No concept I need to explain. Yeah. So here, you know everything here. Yeah. So we move to the next stage, physical law. We need some physical law to model the problem. Modeling step. Okay? So here, the physical law is this, the model. Torricelli's law. Torricelli's law. Okay? Yeah. We need to use this law. Yeah. So what's that? The velocity function, v of t. Yeah. Velocity function. The function. Yeah. We have the formula. Yeah. So that's important. Okay? Equals 0.6 times square root of 2g, g constant, right? Yeah, gravity constant, right? Yeah. So g, gravity constant, given, and a height function h of t. That's the Torricelli's law. Okay? Yeah? So we start with this formula. Yeah. All right. Yeah. So yes, question?
Yes, is that 0.6 and always going to be 0.6?
Yes, always 0.6. Yeah.
Okay.
Yeah.
Thank you.
Yeah, if you apply this law, Torricelli's law, always 0.6. Yeah. Yeah. But if you ask me why 0.6, then, from the experiment, right? Scientific experiment. Okay. Oh, yeah. All right. Yeah. So the acceleration of gravity at the surface of the Earth, we know that constant here, giving 2 units. First, 980 centimeter per second square. Second, 32.17 feet per second square. Okay, yeah. 2 sets of units. Well, but definitely for this particular question, we want to use the first version of constant. Yeah, because we have meter, we have centimeter, right? So the first one more friendly. Yeah. We do not need to convert meter to feet, right? Yeah. All right. Yeah. So next, what is the relationship between the velocity function v of t and h prime of t, rate of change of the height? Yeah. We know the height keeps changing, right? Yeah. The height is decreasing to 0. Decreasing to 0. Okay? From initial value 2.25 meters at the end reduced to 0, and there is a rate of change function, so we use its derivative to represent h prime of t to represent the height. Okay, all right. So here you can see these 2 functions must be related, right? Yeah. These 2 functions must be related. Yeah. Okay, must be related. Yeah. All right? Yeah. Now, next, we want to use another equation to connect. Yeah, because if you only have used this one equation, think about, although we have this nice equation from the Torricelli's law, but in this equation you have 2 unknown functions, right? V function is unknown. H function is unknown. Unknown means the formula is not given. Yeah. What's the formula for the V function? You do not know, right? What is formula of the h function? You do not know. So there are 2 unknown functions involved in one equation. How can you solve it? You cannot solve it. Yeah. 2 unknown functions in one equation. You cannot solve it, right? Yeah. So that means we need to find another function, another unrelated function, independent function. We need to find. Okay, so that's why here we want to explore the relationship between v of t and h prime of t. If you can find this relationship, can you replace v of t by certain form of h prime of t? Then you combine with the first equation, then v of t is gone. We only have equation for h of t, right? Then we can solve it. So that's the idea. So we need another independent equation, okay, representing v of t in a different form. We still represent v of t, but in a different form. Then we can get rid of v of t in the original equation, in the first equation. Yeah. So then we can solve for h of t. That's the idea. Yeah. Yeah. But this is the key step. Okay. Key step. Yeah. So we need to do some further analysis. Yeah. All right. But here we need to use the differential concept. Yeah. Differential. When you establish that equation, we need to do analysis. Yeah. Look at the tank, the change. How does the water inside the tank change? We need to use the, appropriate representation. Yeah. All right, so let me show you. Yeah. Volume change. Yeah. Think about. Let's look at the volume. Volume of the water inside the tank. It changes, right? Volume changes, all right? Yeah. So the volume of water inside the tank, the change amount, you take difference, okay? Yeah. For example, yeah, let's think about T1, T2, okay? At T1, you have one volume, right? At T2, you have another volume. Then you take difference. That's the volume change, okay? Volume change. Then, between T1, T2, the same volume flows out, right? The same volume, yeah. Through the bottom hole, flows out. Same volume, okay? Yeah. So the volume of the water outflowed, that's the same amount of water flows out, okay? Yeah. All right. Then, this time, we need to focus on yeah, so here, volume change between two time instances, okay? Yeah. All right. Yeah. All right, so here, the known value, okay? Diameter we can, because when you talk about the volume, we need to calculate the volume of the cylinder, right? The water, inside the cylinder. To calculate the volume of the cylinder, we need to use, yes. So here, so we use the radius. Big radius, little hole, small radius. Yeah. All right. So we have that. So we are ready to calculate the volume of the cylindrical body of water inside the tank. Yeah. All right. Then, delta V. Delta V is the volume of change. Yeah. So you imagine there are two T instances, T1, T2. Yeah. Between T1, T2, what is the volume change? The difference of the volume, delta V. Okay, delta V. Delta V equals the area of the cylinder, the base, right? The base area of the cylinder, pi capital R squared. It's the base area of the cylinder, right? Yeah. Pi capital R squared times the height change, right? The height, delta H. Yeah. So when you start, you have this formula. Okay? Delta V equals pi capital R squared times delta H. Okay? Yeah. All right. So this is very easy to see. Yeah. But here you use delta. So you know the difference of two numbers. Yeah. The first V number minus second V number, the first H number minus second H number. The difference. Yeah. All right. Yeah. But the question, so here we consider time interval, yeah, a small interval between two time instances. Yeah. Small interval between two time instances. So T1, T2, for example. Okay? Yeah. All right. A small instance. All right. Yeah. Then, yeah, in order to represent the current instance, yeah, so here, because although we use two time instance, but our goal, we want to work on the current instance. current instance, only one time, t. Okay? Current instance, t. Yeah. So we use T1, T2, we approximate. Can we make T1, T2 closer and closer? Then finally they converge to the current instance. How about that? T1, T2, we make them very close, close, close. Yeah. At the end, they converge to 1t, right? So that t, that's our current time instance t. Current time instance t. Think about it this way. So when you start, yeah, you consider two separate t's, T1, T2. Okay? Yeah. So then you get this formula. Okay? You get this formula. Yeah. But this formula, because our goal, we want to look at one particular instance. Yeah. So not two time instances. Not the time interval. Okay? Not the time interval. So we use a time interval to help us get the result of one instance. That idea. Okay? That idea. All right. So we need to take the limit. We need to take the limit. Okay. All right. Yeah. So we, reduce that difference. Delta V, delta H, make it approaches to 0. Okay? Yeah. All right. And the delta H we can represent as the velocity V times delta T. How about that? Can you see that? So here I rewrite, yeah, because the volume of the water outflows, right? So we represent this volume of the water outflowed, right? So how to represent volume of water outflowed? Pi little r squared. The area of that small hole, okay? Area of small hole, that's the cylinder base, right? Base of that cylinder, okay? Yeah. Then velocity is important, right? Velocity times t interval, that's the distance, right? V times delta t, that's the distance, right? That distance is just like a height of the cylinder, right? Height of the cylinder. So the base area times the height of the cylinder, that's the volume, right? Volume, the water flows out, right? Yeah. Imagine that. Think about that. Okay? Yeah. Yeah. All right. So we get this formula. All right? Yeah. Question? Yeah.
So is that saying the value or the velocity at any given point in time?
Oh, yeah. Good question. Oh, let me explain. Yeah. He asked if this v is given any point. Actually, it's not the answer. This v should be the average velocity in that period. Okay? In that delta t period, average v, right? Because that velocity changes. Changes which velocity you want is fair, is the best velocity, average. So this velocity is average, okay? Yeah, that's the critical question. The question he asked, the critical question. So this actually should be the average velocity. Average velocity. Not instant velocity, okay? But when we reduce the time interval, when we make T1, T2 approaches to one T point, this average velocity becomes instant velocity, right? Yeah, that's the reason why we reduce the delta H, delta V. We make T1, T2 approach each other very close and converge to one time instant T, because the average velocity becomes the instant velocity. Okay? Yeah. So that's the reason. Yeah. All right. Then, so let us rewrite this formula, use algebraic property. Pi cancel out. Okay? Yeah, so you look at pi cancel out. Yeah. So then delta H over delta T equals negative. Yeah. So here, negative. Yeah. The reason negative is, we know, the height is reduced, right? Height H becomes smaller and smaller. then it should be negative, right? The height change should be negative, not increasing. If the height is increasing, then the change of height is positive. But now height is decreasing, right? So the change of height is negative. So that's why we added that negative. So yeah, be careful when you set up equation. Yeah, positive, negative. That's important. Yeah. All right. So the negative. Oh, yeah. Actually, here we may need to put a sign, right? Yeah. So this place we may need to put appropriate sign to fix it. Yeah. All right. Yeah. So then negative little r squared over capital R squared times V. Yeah. Then the last step, we make delta H approaches. Oh, let's say when we make a delta T approaches 0. We make delta T approaches 0. We take limit. Okay, take limit. So then we get dt over dh equals negative r squared, little r squared over capital R squared times t, times v. Yeah. And this is the derivative of h. That is the derivative of h. Yeah. Question? Yeah. Question? Yeah. Cool. Yes. Volume, right. Volume approaches 0, but here we take a ratio, okay? When we take a ratio, small amount volume over another small amount, yeah. So take a ratio, yeah. So finally, we get a non-zero representation, yeah. So don't worry. So here, because you have numerator approaches 0, denominator approaches 0, but their quotient does not approach to 0. Yeah. So they have a meaningful quotient. Yeah. All right. Yeah. So this is the new second equation we derived. Okay? Yeah. So we use second equation. Yeah. So we can plug in. Yeah. Because so here, because V, so here we plug in. By Torricelli's law, we replace V, little v, by an expression of H. Yeah. So when you see this equation, V is gone. There is no V. So you only have one function H in this equation. Yeah. Then you can solve it. Okay? Yeah. And we have initial condition. With this initial condition, you can solve it. Okay? Yeah. All right. Yeah. So, any question? Yeah. Ask yourself, can you solve it? Can you? Yeah. So all these numbers given, little r given, capital R given, G known, then solve this different. It's a separable ODE.
The R's and the G are just
Constant,
constants.
yes, constant. All right. Yeah. So then I do not do it here. Yeah. In our textbook there is a detail, okay, solution. Yeah. Here I help you understand the details. Yeah. But in textbook there is one thing. Yeah. Because the textbook in the calculation it converted to the centimeter. Okay. Converted meter to centimeter. Yeah. So this M still use the centimeter. So little r also use the centimeter. Okay, yeah. So then, and when I did calculation myself, I used the meter. Okay, I used the meter, did calculation. Yeah, but the answer is very close. Yeah. Answer is very close. Yeah, the small difference is, due to the computation error, right? Computation error. Yeah, yeah. Remember, last time I talked about we skip some intermediate step. Yeah, the textbook does not skip intermediate step. The textbook calculate every step, find the answer, and I did not do the intermediate step calculation. Okay, I write one formula all the way down to the end. Okay, so only in the last step I plug in the number. So then I try to reduce the error. Yeah. But the textbook, each step find a number. Okay, but number it's an approximate number, right? Yeah, each step approximate number. Then at the end, so the error is different. Yeah, yeah. All right. So when you read, so be aware of that. Yeah. So here I want to save some time, so I want to move to the next topic. So before our break, I want to pretty much complete next topic. Yeah. All right, B.3. In this topic, we will extend our usual method solving separable ODEs to cover a few more forms. Yeah. So let's look at what kind of special forms we can extend. And after the extension, we can make them separable ODEs. Yeah. All right. So let's look at the problem. Yeah. Reduction to separable forms. First, let's look at the separable, our usual separable forms first. Yeah. So to get a separable ODE, usually we need to write our ODE in this form. So here you can see at the two sides of the equality. The left-hand side contains all the terms involving y variable. The right-hand side, it contains all the terms containing x variable. Yeah, so these two variables are separated when we write the equation. Yeah. So the problem is, how many ODEs can we write in this form, right? Yeah. So in general, the number of ODEs that we can write into the separable forms, usually not too many, okay? Yeah. So this form, if we require, we have to stick to this form for the separable ODEs, then it's too limited. Too limited. Yeah. So now we want to extend it. Yeah. So that means even if this form is not satisfied, we have a chance to make it, make it separable. Yeah. So in the first view, it may not be separable, but when we do some special transformations, then we can convert it to a separable ODE form. Yeah. So let's consider. Yeah. So here, let me give you the first form. Yeah. The first form is y prime equals f of parenthesis y over x. Yeah. here you can see inside the parenthesis, there is a special structure. This fractional structure, y over x structure. So this structure is very special. So we want to take advantage of the property of the special structure so that we can, after appropriate transformation, we can convert it to a separable ODE form. Now, so let's consider. Let's take a look how to do the conversion. Here, let me give you a simple example. Here at this place, the function f function equals sine plus, right? Yeah. Okay. So that's the specific f function. Yeah. All right. The first question, is this separable? If we use our standard separable understanding on this equation, so you can see there is no way you can separate y and x, these two variables. No way you can separate. Okay? Yeah. All right. But the good thing is we have a chance. We can take advantage of the special structure of the part inside the parenthesis. Yeah, this part. Yeah. All right. So what to do? Yeah. All right. In this question, f is very simple. Yeah. But in the general situation, f could be very complicated. Yeah. And to solve question with this structure, we need to introduce a new variable u. Yeah. So we make this new variable u equal y over x. Yeah. So here you can get the main idea. In this way, we can make everything inside the parenthesis one single variable. Just one single variable. Okay? Yeah? All right. All right. So then the right-hand side is very simple. It becomes f of u. Yeah. But the left-hand side, we also need to change. Y prime should have a different form. Yeah. So let's look at the y prime part. Yeah. All right. So from the initial assumption, so u equals y over x, we can write y equals ux. Yeah. So it is a product of two variables. So when we take y prime, we can use the product rule of the derivative. Product rule of the derivative formula. Yeah. So that is y prime equals u prime times x plus u. Yeah. So let's replace the right-hand side y prime in the original equation to this new form. Right? Yeah. So let's update the form. We will get u prime x plus u equals f of u. Now, you examine this equation again and see if it is separable. It's easy to see it. It's separable, right? Although you need to do some transformation a little bit, yeah, but it's pretty easy. So you can separate u and x in the desired way, right? Yeah. Left-hand side, all the terms containing u variable. Right-hand side, all the terms containing x variable. Yeah. after that, you just, take the integral. Yeah, so that's the, integration step. Yeah. All right, so let's get back to the previous simple example. So now we can solve it. Yeah. Because f of u equals sine u plus u, right? Yeah. But left-hand side, at the denominator, we need to calculate f of u minus u. Yeah. So this f of u minus u, then that u term is gone. So what do you see? du over sine of u at the left-hand side. Yeah. So right-hand side, very simple. Yeah. Then you just take integral, both sides. Yeah. All right. Yeah. Yeah. So I do not need to complete it. Yeah. But you need to, check by yourselves, see if you can calculate the integrals of the left-hand side. All right. How about the form? Yeah. So I may change the structure inside the parenthesis, slightly different structure. Y over kx. How about that? K. Okay. K is a non-zero constant. Okay. Can we still apply this technique? All right. Yeah. Think about. Yeah. Think about. Yeah. Another way. Also think about. How about this? I want to change, for different structure. Y squared over x. How about that? Okay. Yeah. Yeah. Things like that. Yeah. Think about it. Is it possible we can still use this, similar technique? Yeah. Variable substitution. This technique still works or not, right? Yeah. Think about that. That's the first example. Yeah. Second one. Yeah. Second one. Yeah. Actually, the second one is here. You can see the form is slightly different. Yeah. But here, to go a little faster, let me just use two concrete examples to show you the main idea. Yeah. All right. So let's solve the first example. Yeah. This is a first order ODE. Yeah. All right. To solve it, first we need to do some simplification. Yeah. So the first simplification, we want to write it as a explicit form. So that is y prime equals something. Right? So y prime equals y squared minus x squared over 2xy. Yeah. But we want to further simplify it. Yeah. So here we do the simplification like this. Yeah. I remember in class, Lucas asked me how to get this step. Yeah. So here, let me show you. Yeah. To get that, can we split the two terms in the numerator separately by the property of algebraic property? Yeah. So for the fractional form, yeah. So that is, we can write y squared over the denominator 2xy first, minus the second part, x squared over the denominator 2xy. Right? Yeah. But for the first term, we can do cancellation, right? Yeah. Y can be canceled out. So you get a y over 2x. Yeah. But the second term, we can do cancellation on x. X cancel out. So we get x over 2y. Yeah. After we convert it to this form, so then we can use u variable substitution. This time, yeah, the same, y over x. Yeah. All right. Then y prime equals u prime x plus u. Yeah. And the right-hand side, the first term, u over 2. The second term, 1, yeah, actually the reciprocal of u, right? Yeah. So x over y equals 1 over u. Yeah. Then 1/2. Then we multiply 1/2 to it. Yeah. All right. So after this update, yeah, so we can get a separable form. Yeah. So then, yeah, we write it as a separable standard form, separable. Yeah. So after that, we can take integral both sides. Yeah. Here I leave it to you to complete. Yeah. All right. So that's the first example. The second example. Yeah. This time, although the structure inside parentheses is different, yeah, but we can still use the similar idea, introduce a new variable to represent everything inside the parentheses, u plus 4x. Yeah. Then we take derivative, y prime equals u prime minus 4. Yeah. All right? Yeah. Then the right-hand side, simply u squared. Yeah. All right? So then you can see it's very easy. We can write it as a standard separable form, like this. Yeah. All right. Yeah. After that, we take integral both sides. So I leave the remaining part to you as practice. Yeah. So get yourselves familiar with many commonly used integral formulas. Yeah. All right. So now we complete part B.